All right, so inverses is what we're going to talk about today, and one-to-one function. Okay, and how we determine whether functions are inverse to one another, and we determine whether a function is one-to-one. It says the inverse of a function is a rule that acts on the output of the function and produces the corresponding input. Okay, I'll talk maybe about a different way of talking about that and phrasing that here in a little bit. It says the inverse undoes or reverses what the function has done. Undoes or reverses what the function has done. It says not all functions have inverses. Those that do are called one-to-one. Okay, so I'm going to open the window because it's hot up here. It says the inverse of a function is a rule that undoes an original function. Okay, think about what you guys know operational-wise. Adding and subtracting, do they undo each other? Yeah. Multiplying and dividing, do they undo each other? Yeah. Okay. So inverses are the same concept, but they're functions. Okay. What an inverse should do is you should be able to start with some value a. Okay. So I'm going to start with a function. Don't care what the rule is right now, but I'm going to run a through it. And let's say it spits out b. Okay. So I start with a, run it through a function, I get an output of b. I'm then going to take b and run it through a second function g. Okay. If f and g are inverses, then g better undo what f did. So g better take b and turn it back into a. Okay? So if you have two functions, f and g, and they are in fact inverses of one another, you should be able to take an input, an original input, run it through one of the functions, get an output. Take that output, run it through your second function, and your second output should correspond to your original input. And that's what that first phrase is saying. The inverse of a function is a rule that acts on the output of the function and produces the corresponding input. Okay? These two things should be the same when I run that initial output through my second function. Okay? And that means that they undo each other. They are inverses. Okay? Some graphical or visual ways of seeing what we call one-to-one is what we're seeing here. These are rules. We talk about these. These are just rules. These are functions. They're mappings. Sometimes called arrow diagrams. They're saying, and we talked about, I guess, this one earlier, because this one is, and we saw this at the beginning of the chapter. That is a function. Okay, we're saying that if I take 4, you know that it's going to go to 10, right? So an x value of 4 is going to get paired up with a y value of 10. An x value of 3 is going to get paired up with a y value of 4. An x value of 2 is going to get paired up with a y value of 4. And an x value of 1 is going to get paired up with a y value of 2. Okay? That is a function because we said that for every x value, every time I take 4, you should get one y value, and everybody knows what that one y value is, right? Okay? I should take what we had for the rule for a function said every x value has one and only one y value. Every x value has one and only one y value. And 4 is only going to 10, right? 3 is only going to 4. 2 is only going to 4. 1 is only going to 2. Does that make sense? We don't have arrows from 1 going to 2 and 4. Okay? We don't have arrows from 2 going to 4 and 10. Okay? So that is a function. If we graph those points, 4, 10, 3, 4, 2, 4, 1, 2, passes a vertical line test. Okay? However, that function is not one-to-one. Okay? This function over here is one-to-one. And you can maybe kind of investigate and look at that and see the discrepancies. Okay? The reason the one on the right is not one-to-one is that situation right there when you have two x values going to the same y value. Okay? We don't have that going on the left, right? Okay? Every x value gets paired up with one y value, but likewise, every y value gets paired up with only one x value, right? Over here, we had a y value getting paired up with two x values. Okay? So, the one on the left is said to be one-to-one. Okay? Meaning that if I tell you guys, let's just look at it maybe with a more concrete function. Let's look at So we got the function f of x equals x squared. This is a function because no matter what x value I give you an x value of 2, you can tell me the one y value of 4 that goes with it, right? I'll never give half of you the value 2 for an x value, and you give me 4, and I tell the other half of the class, here's your x value of 2, and they give me something back different, okay? Everybody's going to give me back 4. And that's what makes it a function. What makes it one-to-one or not one-to-one is the fact that if I give you a point, 2, 4, and negative 2, 4, okay? If I say, look at this function, look at this graph, and provide me the x value now, okay? So give me the x value that gets paired up with 4, what's the problem? There's two options, right? Half of you are going to give me 2, the other half is going to give me negative 2, right? Okay? So that is what the one-to-one thing is talking about. This function is not one-to-one. Because not everybody's going to give me the same y value, or sorry, same x value back for that y value of 4, right? Okay? So this picture here, this graph, would be comparable to what's going on right here. Okay? Obviously we've got a 3 and a 2 instead of a negative 2 and a positive 2. But that would be what's going on in that curve. Does that make sense? Okay. The phrasing or the definition of one-to-one functions is written here, and it might be kind of weird to think about and how they write this, but it says a function with domain A is called a one-to-one function if no two elements of A have the same image. Okay. Elements of A we're going to think about as being our x values. Okay? The image is the y values, or the f of x values. Okay? And if we look at this phrase here, what it means algebraically is this right here. Okay? It says f of x sub 1, so your y value that is paired up with some x value, is different than the y value that comes from a different x value. Okay? Whenever your two x values are different. So, I should be able to give you an x value. Okay? If a function is one-to-one, I should be able to give you an x value, and you give me the one and only one y value that goes with it. Okay? Or I should be able to give you a y value, and you tell me the one and only one x value that goes with it. Does that kind of make sense? Okay? If we read those two phrases down at the bottom, I think that's kind of a better way of thinking about it. It says for every x value, there is one and only one resulting y value that pairs with it. And that was the criteria to make it a function back in Algebra 2 when you learned the vertical line test. Okay? Okay, so not all functions are one-to-one, so there has to be additional criteria to make it one-to-one, and that's the additional criteria there. Is for every y value, or if you want to still call it f of x, that's fine, there is one and only one x value that pairs with it. And that's why the x squared function is not one-to-one. So when I give you a y value of 4, there is not one and only one x value that pairs with it. There's 2, right? Positive 2 and negative 2 pair with it. Okay? So that violates what we end up calling the horizontal line test. It violates the idea of being a one-to-one function. Okay? This idea, I think what I've circled here can be somewhat problematic for some people, but if we look at it this way, okay, this here is x, call that x sub 2, call this here x sub 1. Would you agree that those two things are different? Negative 2 and positive 2, they are different, right? That's all that symbolism is saying there for us. If I look at this point here, the y value, okay, that is f of x sub 1. That is f of x sub 2, right? Okay? However, they are, terrible not equal sign, they are not different. They are the same, right? They are both 4, okay? So that does not, and we said this function is not one-to-one, so that does not satisfy that definition where when your x's are different, your y's have to be different. And it's actually a two-way street, so when your y's are different, your x's are different, okay? If I give you something like this, Okay, now I give you an x value, x sub 1 right there, and I give you an x sub 2 right there. They are different, right? X sub 1 does not equal x sub 2. Positive 2 is different than negative 2. Look at f of x sub 1 and look at f of x sub 2. Those y values, are they unequal? Yes. Okay? And that relationship for any x1 and x2 that I choose on that entire graph, and then for the y values that get paired with it, f of x sub 1 and f of x sub 2, that relationship of the x's not being the same is going to provide always your y's to be different. Okay? And that function then is 1 to 1. So x cubed is a 1 to 1 function. X squared is not. What is the difference between this, between these two functions, x squared and x cubed? X cubed, if you think about it, going back to what we talked about earlier in the chapter, if I go left to right on this graph, and as I read it, okay, and I'm just going to drag a point around here, what is this point in regards to its y value? What is this point always doing on that curve? What is that feature when the x value moves from left to right? Let me attach the point. That work? There we go. As I move it to left to right, okay, notice look over here, you x values. Yeah, are those x values left to right getting bigger and bigger?
Yeah.
Okay, so as my x values left to right are getting bigger and bigger, what is happening to your y values? Bigger and bigger. So what was the word that we used for that? The function is increasing. Okay? When your graph is increasing, okay, always increasing, your function is 1 to 1. Okay? If I go to x squared, okay, we see here that we're decreasing, 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 now increasing, right? So we failed the relationship of being 1 to 1 because we're doing both behaviors. Okay? A function that is only increasing or only decreasing will always be 1 to 1. Okay? And the idea is, we call it the, bring this up, we call it the horizontal line test, which is applied the exact same way that you guys apply the vertical line test. Okay? To fail the vertical line test, you had to intersect your curve more than once, right? The vertical line. Okay. Well, to fail the horizontal line test, you have to draw any horizontal line, and your curve has to intersect it 2 times. Okay. The logic of, and this picture here shows us failing the horizontal line test because we're seeing x1 and x2 are not the same, right? Okay. However, what is the relationship between f of x sub 1 and f of x sub 2? At those 2 spots, those values would be equal, right? Okay, so it's showing that you violate the definition of what we set up to be 1 to 1. So the horizontal line test is a quick rule for us to determine whether a function is 1 to 1 or not graphically. And if you think about it, okay, if I start drawing a function, I don't even care what that function looks like, but as long as I keep increasing, okay, that function right now is 1 to 1, right? Every horizontal line that I ever create is going to only intersect that one time, right? What has to happen for me to fail the horizontal line test is that curve eventually needs to bend back down on itself, right? Because I'm passing here, passing here, passing there, passing there. But right there, because it bent back down, it changed from increasing and then started to decrease, we will fail the horizontal line test, right? So we learn that anything that is always increasing or always decreasing will always pass the horizontal line test and therefore will always be 1 to 1. Okay? So the horizontal line test is a tool for us to check this rule right here. Okay? When your y values are different for whenever your x sub 1 and x sub 2 are different. Okay? Something I told the last class, and I think it's beneficial for us to realize, we have graphs of things that are not functions, right? A circle is not a function, correct? Okay? So when they ask us to check to see if a function is 1-to-1. Okay? The only things right now that we can talk about that can be 1-to-1 are functions. Okay? So when they say this, check to see if this function is 1-to-1, it has already passed the vertical line test, right? So you don't need to apply it again. Just go straight to the horizontal line test. Okay? Now if they say, is this rule 1-to-1? Okay? Is this rule 1-to-1, or is this graph 1-to-1, or something like that? Is this relation 1-to-1? The first thing you have to do is to check to see if it is a function, because only functions can become 1-to-1, right? So once I classify it now as a function, now I can take that extra step and classify it as 1-to-1 using the horizontal line test. Okay? So these two tests, the horizontal line test and the vertical line test, go together. Okay? They're very useful together. But if I look at this example, for instance, it says, is the function f of x equals x cubed 1-to-1? I already know it's a function. I already know they're telling me using the words function, they've told me it passed the 1-to-1, or sorry, it passed the vertical line test. Okay? If they just said, and really, that notation tells me it's a function too. But if they just said y equals x cubed, they say, is y equals x cubed 1-to-1? The first thing we have to do, graph x cubed, or think about x cubed, know what its structure looks like, and see if it passed the vertical line test, classify as a function. It will be, and then we can go and do the horizontal line test. Does that kind of make sense? They're saving you some work here. Saving you some work here when they already tell you it's a function. Okay? So all we have to do then is we have to put in horizontal lines and let that horizontal line kind of slide up and down as much as we need it to, and see that everywhere that I intersect my graph, I'm only doing it at one spot. Okay? There is some more stuff behind here. I've moved this from the last class. It says, first solution, first option is if x sub 1 and x sub 2 are different, then you can notice that x cubed is different for x sub 1 and x cubed is different for that x sub 2. There's no number, you think about it logically, there's no number in the number system that when you cube it, you get the same value that you get when you take another number and cube it. So think about like taking 2 and a number like 5. If I cube 2, I get 8, right? There is no other number in the number system that I can cube and get 8. All right? 5 goes to 125, right? There's no other number in the number system that I can cube and get 125. So that's maybe one argument that we could say to prove algebraically that a function is 1-to-1. Conversely, think about x squared. And why x squared is not 1-to-1. Okay? Think about a number on your number line that you can square to get 9. What would be one of those numbers? 3. Okay? But is there another number on your number line that you can square to get 9? -3, right? And that's the idea that we fail the horizontal line test. We're saying that x sub 1 and x sub 2 are different, 3 and -3. But that would tell us that x sub 1 squared is equal to x sub 2 squared, and that'd be a problem. Okay, so that'd be not 1-to-1. Somebody in the last class kind of looked at this and said, well, it kind of looks like my graph here kind of plateaus off here at 0, 0, right? Okay, and it starts to look like it's even a horizontal curve there, sorry, horizontal section of that curve. But if we think about what is actually going on there, we got very, very small, around 0, 0, we got very, very small x values, right? Okay. Well, if I take point, I'll just start with 0, and then, so we'll start with x values, and then we'll get our y values, or f of x values. 0 cubed is 0. Okay, if I go 0.0001, and then go 0.0001 cubed, okay, that is going to be, hopefully you understand that whatever that calculates to be is going to be different than that number, right? Does that kind of make sense? Okay. This is going to be a very small number, but that one's going to be even smaller, correct? Okay. And then if I start getting, so that's getting closer and closer to 0, but if I start moving away from 0, maybe I go 0.1, or let's just go 0.01, 0.01 cubed, 0.1, 0.1 cubed, okay? All of these numbers, all those y values are going to be different. They're not going to be the same. And you see then that because all these x values were different, that means x 1 does not equal x2, and over here means f of x sub 1 does not equal f of x sub 2. Okay? So it does maintain that one-to-one relationship kind of in that region there that looks like graphically we might fail it. Okay? So it's just something to think about as you're doing some of these problems. Let's see here. Talked about that already. When a function is only increasing or only decreasing, that's a good way for you to recognize that it is going to be one-to-one. Okay? Now here's what's, one-to-one functions is very, very important to understand. Okay? Because that's kind of the springboard into talking about inverse functions and what inverse functions can do. Okay? What we learn is that functions like f that have an inverse, okay, because not every function is going to have an inverse, but the functions that do have inverses turn out to be one-to-one functions. Okay? Only one-to-one functions have inverses. Okay? And says one-to-one functions are important because they are precisely the functions that possess inverse functions according to the following definition. Okay? Here it says let f be a one-to-one function with domain A and range B. So x values that come from some set A, and they get paired up with some y value that comes from some set B. So then its inverse function, where we write it as f and then a superscript of a -1. Okay, and you've seen that other places. We'll talk about that here in a moment. It says function f inverse has domain B in range A. Okay, so your original function f has domain A in range B, and its inverse has domain B in range A. You see that they flipped, right? Okay, this was A and B, and this becomes B and A. And it's defined by this rule here. Okay, now I don't like that rule written that way. I prefer it this way. I prefer to go to f of x equals y. If it, does anybody know what that double arrow stands for? No. Talk about in geometry. If and only if. Okay. So that means I can read this left and right to left, right? So it allows me to use this kind of symmetry property and flip-flop that statement. What we're saying here, these are inverses. If we have one-to-one functions, these are inverses because I take an x value, get an output. Okay? Take that output, run it through what your inverse is, and you get back to the corresponding input that we started with, right? Okay? And that kind of matches up with that f of a equals b and g of b equals a statement that we made at the beginning of the period. Okay? But that should have happened for any, here it says for any y in b, but no matter what x value I choose, if I write it this way, okay, for every x value I choose, this should be maintained. Okay? Giving you the picture of what inverses do visually. I know you guys can download these and look at these on your own, but I know sitting in the back it's kind of maybe hard to see some of the notation that he used. But set A, set B. I've got a rule that takes takes x, run it through the rule f, and it puts me to a value in B, right? It takes me to a range value in B. I then take that value and run it through f inverse, and it gets me back to where I started. Okay? We talked about functions, and I think we talked about it in this class a couple days ago. If I were to have like a food processor, and I take an apple and put it in a food processor, it gives me applesauce, right? So that's kind of like what a function does. Take an input value, it rearranges it, and gives you an output, right? Okay? So my applesauce is my output. Well, inverses, if I had an inverse machine of that food processor, what it would do is I'd be able to take that applesauce, put it into another machine, and that machine kicks out to me what? A full apple. Okay, it gets me back to what I started with. Okay, that's the kind of the visual that you're thinking about with functions. Okay, they define this mapping here, or this arrow diagram, this way. It says domain of f inverse equals the range of f. Okay, so if you know the y values, the range of your original function f, you automatically know you know the domain values of your inverse. Okay? If you know the range values of f inverse are equal to the domain values of f. So now if you know your x values for your domain, for your original function, you should know then the range values of its inverse. Okay? Now, writing that may be a little clearer, a little bit easier to visualize. Okay? Those two statements lead you to this argument here. If you have the point A comma B on f, on your original function, then the point B comma A is on f inverse. Okay? They just flip, the domains and the range just flip, right? A is a domain here, A is a domain there, and a range there. Okay? And if we abide by those two rules, then on f inverse, A becomes a range value over here, and B becomes a domain value over there, and the inverse. Kind of graphically speaking then, if we were to look at one of these functions, let me clean this up a little bit. We know x cubed is 1 to 1. We've already talked about that. Okay? X cubed is 1 to 1. And it looks like that. Okay? What this means to me then, that if I pick a point off of x cubed, maybe 2 comma 8, we know that exists, right? Okay? Then on its inverse, I should have the point 8 comma 2. And that point should show up on the inverse. Okay? If I have 1, 1, it's kind of a trivial, easy point, but that's on my original function. Then when I flip it, 1, 1 is on the other one, right? If I have 3, 27, then I should have 27, comma 3. Okay? You see that 3 27's up here, 27, 3 will be down here. Okay? Now what this app allows us to do, I've set it up to where it will take, you see that black dot B kind of scrolling through there? Okay? On the green curve. It is going to take it, it's at 2.2, comma 10.65. And I ask it to flip those two ordered pairs and create the point down here, it's actually right there where my cursor is, of 10.65, comma 2.2. Does that make sense? Okay? So when I run that through, it kind of looks like that curve there. Okay? So, and let me actually, just to get it to be a little bit less kind of gaps there, let's go 0.025. Oh, that didn't work. But as I move that through, we start to see, let me zoom in a little bit, you can maybe get a better, cleaner picture. But it provides you the graph of the inverse. Okay? The graph of the inverse is that red curve. We put a solid line through that solid curve through that red set of points. We would get our inverse. Okay? Now, what's interesting about that inverse is that if I had, this is something we learned from geometry. If I have a point up here, A, comma B, and that gives me a point down here, B, comma A. Okay? What that tells us geometrically is that that is a reflection across the line y equals x. And that's why I've got that dotted line there. That is the line y equals x. And it is a reflection because if I put in that argument right there, the distance from this point here to line y equals x is 2.85. And then from there to this point over here is still 2.85. And with reflections, we know that distance is preserved or saved. Doesn't change. And as I move that slider around, we get then the picture, the image of that function. We see that relationship exists about moving those points in regards to the distance from the line y equals x. Does that kind of make sense? Okay. Now here's the thing. This tool does have kind of its flaws because it's not set up to know what is a function and what is not a function. Okay. It's not set up to know what has an inverse and what doesn't have an inverse. So let me clear some points out here that I don't want anymore. For instance, if I take x squared, all right, and really what this graph is doing, what this picture is doing, is it's showing you the reflection of x squared over the line y equals x. So if I kind of trace that out, we get that image there, right? Now the problem with this image, one, the graph of x squared is not 1 to 1, right? And because it's not 1 to 1, when I find what I think may be the inverse graph, what test does that inverse graph fail? The red one's going to fail the vertical line test, right? Okay. Therefore, the red one is not a what? Function. And that's why we need our original function to be 1 to 1, because then if it's 1 to 1, when you reflect it, the image that is reflected will be something that passes the vertical line test. It will be a function. Okay? But we know something. We know a function or a rule that undoes x squared, right? What is that rule that undoes x squared? Square root of x, right? And if I look at this red curve, the square root of x is simply that top portion, right? Okay? So let's think about how we could just get that top portion to get reflected. The only way I can get that top portion just to be reflected, which would be that green portion, that right-hand side, right, of x squared. So what I need to do for x squared to have an inverse, we actually have to say that we want to restrict its domain to that. Okay? So now, when I run through this, does the red curve now pass the vertical line test? Yes. Yeah. Okay? So, when we say that x squared and square root of x are inverses, we should probably better clarify that and say x squared and radical x or square root of x are only inverses provided that x is greater than or equal to 0. Does that make sense? Okay. And you see then that I've got the point, still relationship of 3.6 comma 12.96, and then 12.96 comma 3.6. So they flip-flop spots. Now what we want to do, so we understand maybe the graphical approach of inverses. We want to be able to answer a few questions. Okay. Now that we've seen that visual, maybe this question is kind of easy to answer. It says if f of 1 is 5, and f of 3 is 7, and f of 8 is negative 10, okay? And if we graph those points, they've passed the vertical line test, so they are a function. They passed the horizontal line test, so they are 1 to 1, okay? Then there must exist a rule that takes f inverse of 5 and provides me something back. Well, what do inverses do? If this is an x value A and a y value B, when I run it through the inverse should have B comma A, right? Is that going to make sense? So what would, if I plugged in 1 and got 5 back, and the inverse I plugged 5, it should get 1 back. So f inverse of 5 is 1, f inverse of 7 is 3, and f inverse of negative 10 is 8. Okay, so you're going to see a handful of questions on your homework. You might see one on your test and at the end of this week that kind of asks you to do that. Okay. Hopefully, it's kind of a simple process, a simple understanding, and just trying to make sure you understand that the x and the y's flip for inverses. Okay. Just real quick before we go too far, don't mistakenly think that the negative 1 in the notation is an exponent. It's just a superscript. It's part of the name for f. So f inverse, we don't read it f to the negative 1, right? Because that makes it think that it is, in fact, an exponent. So we read it as a negative 1 here. As a superscript has the word inverse attached to it. So we go f inverse for our function, okay? So f inverse of x does not mean 1 over f of x. Because that's what you would do with a negative exponent, right? Okay, if I had x to the negative first, you would write that as 1 over x, right? So if I have f inverse to the x, I want you to understand that that is not 1 over the function f of x, okay? I do see people periodically doing that because they forget that notation, okay? If we wanted to do this, if we wanted to make that reciprocal, we would take f of x, whatever that function is, block it off in its own set of parentheses, and put a negative 1 as an exponent out there. Okay? That would then give you 1 over f of x. You've seen it before. If you get your calculator, we did this in Algebra 2, did it in geometry. There's a sine function, a cosine function on your calculator, right? And a sine function, cosine function, tangent function, they give you the relation. They give you a ratio of the adjacent side divided by the hypotenuse, the opposite side divided by hypotenuse, and the opposite side divided by adjacent for any right triangle, right? Okay. Well, if I use the sine inverse now gives me the angle measurement attached to one of those ratios. Okay. So it basically undoes what the sine and cosine buttons do. However, if you know anything about sine, you guys get the sine and cosine in physics yet and graph them?
Yes.
Okay, so you know what they look like, right?
Yes, sir.
Alright, so you know that function there. Right? Alright? Does that pass the horizontal line test?
Yeah. No way, no, it passes the vertical line.
It passes the vertical line test, so it is a function. But it fails the horizontal line test. Okay? But what we know is that our calculator has that function, the sine inverse on it, right? So what happens is that we restrict this to what happens to be negative pi divided by 2 less than x less than pi over 2. If we do that, okay, so we take the original function sine of x, which is going on forever, right? And we just look at a little small sliver of it, and then does that pass the horizontal line test? It does. So that's what those are the values that your calculator is using and talking about when you use the sine inverse key. But that's where we're going with this stuff into the trigonometry course after Christmas. We're going to need to know what inverses mean. We need to know what one-to-one means so we can do that kind of stuff. Okay. All right. So in the next couple minutes, I want to do a few examples of how we do this algebraically. Instead of looking at a graph and graphing two functions off of one another and seeing if they endless amount of points flip-flop and become that or have that relationship of being inverses is very hard to do sometimes, very complex. So we want to be able to do it algebraically. Okay, sometimes they refer to it as analytically. Okay, it simply says by definition the inverse function f inverse undoes what f does. If we start with x, apply to it some function f. Take that output, apply to it some function f inverse. We should arrive back at x, right? Okay? Well, if you think about what they're saying here, they're saying if you have f of x and f inverse of x, take some x value, let's say x is 2. Plug 2 in, it should spit back some output, let's say it spits out 4. We now take 4, plug it in there, and what should spit back? 2. Okay? What have we been doing in the last couple days? Hopefully you can draw a comparison. If I gave you f of x is equal to, just go 2x, and g of x is equal to x squared. If I asked you to find f of g of 2, could you take 2, plug it into g, get 4 back, right? Then you take that 4 and you plug it into f and get 8 back, right? So when I asked you to do this here with f and f inverse, this was the composition, right? Is that what this is? Yeah, when they're asking you or they're telling you that you're taking a value x, plugging it into f, getting an output, taking that output, run it through another function and get a different output, that's a composition. Okay? It's just a unique composition in that if they are inverses, you will get back to what you started with. Okay? So if we start with x, and these two functions, f and f inverse, are legitimately inverses of one another, if you start with x, apply both those rules to whatever that number was, you should get back to the same x you started with. Get back to the same number you started with. Okay? So what we're going to do is we're going to apply these rules. To see if two functions are inverses, we're going to find out that f inverse of x, simplifies to x, and then f inverse of f of x simplifies to x. Okay? We need to do both. We need to make sure that both functions are inverses of one another, right? So we want to make sure that doing both those says f inverse is the inverse of f, and f is the inverse of f inverse. Okay? Now a lot of times in your examples that they give you, they don't necessarily use f and f inverse. They might use f and g. Okay? Usually if they use f and f inverse, the question is verify that these are inverse of one another. So they're telling you f and f inverse are inverses, but they want you to verify, show the algebra that shows why they're inverses. Here it just says, are they inverses? Are f and g inverses? Well, if f and g are inverses, they should still have this relationship that if one of them is the inverse of the other, if f of g of x, if those are inverses, we should get x back, right? And flip-flop it. If those are inverses in that order, we should still get x back. Okay? So it doesn't always have to be f and f inverse. Okay? This is kind of telling you we already know them to be inverses, just show the work that proves it. Here is, are they inverses? Ask that question, answer that question, but then also still at the same time show the work that proves it. So what we're going to do is we're going to do that with those two functions. We'll do two examples of this. Negative 4x plus 8 and negative 1/4 x plus 2. They're both linear, okay? So linear functions are kind of boring to deal with because the algebra is pretty easy. But we're going to apply this first rule. We go f of g of x. F g becomes negative 1/4 x plus 2, right? All right. So that's the first step that we've always done with compositions. Now, I'm going to go to the f function, and wherever I see x, I'm going to replace it with that. So it's going to look like this. Wherever I see x, I'm going to go negative 4. Wherever I see x, it's going to become negative 1/4 x plus 2. And I got my plus 8, right? My hopes are that you recognize that this negative 4 and this plus 8 are kind of, we talked about yesterday, it's going to be in the outer shell of that function f. Okay, where x was, all you did is replace it with what we have said that g of x was. Okay, now that should produce something that we can simplify. If I distribute there, what do I get? X minus 8 plus 8, what's that give me? X. Okay? So, that is not enough to show that they are inverses. Okay? It's only half the procedure. Okay? Because sometimes you will see that you go through, you pair them up one way, you get X going through it one route, and you might get like negative X going through it the other route. Okay? Or you might get 1 over X going the other route, something like that. So you've got to make sure that you do both comparisons here. So now we go g of f of x. Okay, f of x is negative 4x plus 8. Okay, so now I'm going to go to g, which has the makeup of negative 1/4, whatever x is, and then plus 2. But we now know x is negative 4x plus 8. Distribute, negative 1/4 times negative 4 is 1 again. Distribute, I get negative 2. Add 2, what's that give me? X. Okay? So what we have proven here, guys, is if I take a value like 3, and I should be able to run it through those functions and get back 3. And I should be able to do it in this order, put 3 in, and get back 3. But to prove that they are inverses, I've only shown that, 3 gets back 3, right? I need to show that they're inverses. I need to show that that exists for the entire number line. Well, how many numbers are there on the number line? Infinite. So I need to replace that with an infinite number of values and recognize that we get that relationship every single time. Well, that's infeasible. That's not going to be something you can do physically, right? So algebraically, though, we say, okay, well, that's just some arbitrary value x. See that we get some arbitrary value x back. If we see that relationship, then we know that regardless of what x is, 3, 4, 5, or any of the infinite numbers on the number line, then in fact that is going to provide us inverses in those two relationships, those two rules. One more real quick, because this one is kind of an indicator that we would call our marker that tells us that they are not functions. First of all, notice that they have a restriction here, because we know the parabola is not 1-to-1, right? So whenever a function is not 1-to-1, by itself in its entirety across this whole domain, they will restrict it so it becomes 1-to-1. So if I say x squared plus 5, okay, it looks like that, it's not 1-to-1, right? So they say provided we just look then at that portion, because now that portion is going to be 1-to-1. Okay? So that's why that x is greater than or equal to 0 is there. But the same rule applies. Let's go f of g of x and see if that's x. And if it is, we'll then see if g of f of x is equal to x. So just doing the first one, we got f. G of x is radical x minus 5, right? I'm going to plug that into f, which is of that format, right? But now the x is radical x minus 5. We'll go through and simplify that. I've got to FOIL this, right? That's where you got to be careful. If I got to FOIL that, I've got x minus 10 radical x plus 25 plus 5, right? Is that going to simplify down to x?
No.
No. Okay. So that is shown to be false. So are those inverses? No. And you can graph those and recognize that they are indeed not inverses. Okay. We'll pick up with this tomorrow. There is going to be a web assignment that I put up here in a moment, but it's not going to be due tomorrow.
Theoretically, could you just graph it on the calculator and find out?
Yeah.